Hello everyone, it's Andres again. In the next video I'm going to talk about what's a great circle, what's a small circle, and I'm going to define what's a spherical triangle and what is an angle in a spherical triangle and what is a side in a spherical triangle. So let me begin talking about what's a great circle. So imagine that you trace a circle through the surface of the sphere. If the plane of this circle contains the center of this sphere, we're going to have that this is going to be a great circle. On the other hand, if this circle don't contain the center of the sphere, this is going to be a small circle. So we can see some interesting properties of this. If we have, for example, a trajectory over the surface of a sphere that's a circle, if we have 2 points Q and Q prime that are not antipodal, we're going to have that this is going to be the shortest distance between these 2 points. You can imagine this in an intuitive way between the relationship of this and the Pythagorean theorem, and we can see that if they are antipodal, that's not necessarily because we can vary the angle of inclination of the great circle, and we are going to have that these are not going to define unique trajectory necessarily. But in the case that they are not antipodal, they are going to define a unique trajectory. And know that this is a good intuitive explanation because of the shortest distance, because you can think that in a sphere, if you go near and near, you go to nearer points, what you are going to have is like lines in the nearer points. So you can see, okay, if for shortest distance this is going to work, why not for distance that are greater? So you can think that in an intuitive way. Now let's talk about sides and angles in a spherical triangle. So first of all, what's a spherical triangle? The form that forms because of the intersection of 3 great circles is a spherical triangle. That's the form that we have here. This is a spherical triangle. So from this figure we can define some of their properties. That's going to be the sides and also the angle. So to define the sides, there's no that they are going to correspond to the length of the arcs. So to see what are the sides, we can see that, for example, if we have an angle alpha here, this is going to be alpha times r, in the same way that if I have an angle beta here, this is going to be r times beta. And if I have an angle here, what we have is that, let's suppose that this angle is c, this distance is going to be times r. So in this way, if r is equal to 1, we're going to have that the length of the r's are going to be the length of the arcs are going to be alpha, beta, and z. So in this way we can define the sides. So now let us talk about the angle of a spherical triangle. By the way, and these sides are defined by this this angle that we have, central angle. So now let's talk about the angles in a spherical triangle. We have, for example, here an angle O, and we want to define how is this angle formed. So let's suppose that we have this surface that is like a pyramid, or a portion of our sphere. So we can trace here a plane, and we can trace here another plane. Now the angle between the intersection of these 2 planes is what is going to define the angle in the spherical triangle. Another way to see it is that if you go in this direction, and you have and you go 2 in this direction, when you arrive to this point, you're going to have two tangents that go in this direction. Yeah, if you zoom, what you're going to have is something like this, and this is going to define also the angle alpha that's going to be opposite by the vertex with the angle alpha that we need here. So this is another way to see it. So with these concepts clear, let us proceed to deduce what's the area of a spherical triangle. So let us know that we have this, that is like the area that forms between two parts, half parts of a great circle, and we define this as a lune. Know that we have by proportions that for 2p we have an area of 4 times p times r to the 2, and so for 2i a, that's going to correspond also to the lune that's on the other side. We're going to have a proportion of 2a times divided 2p times 4 times p2 times r to the 2. In this way, we're going to have that's the correspondence proportion or the correspondence area to 2a. So in this way, we can easily define what is going to be the area of a spherical triangle, because we're going to use the following argument. Imagine that we have here a spherical triangle, as you can see. This is our spherical triangle. So let us see that here we have a lune that's going to be due to A, and we have another lune here that's going to correspond to A too. Yeah, this lune corresponds to A and this corresponds to A. We have, for example, here another lune that corresponds to B, because these angles are opposite by the vertex. These two are opposite by the vertices. This is B2, and this lune corresponds to V2. So in this way, we can repeat the reasoning and zoom the area of the lunes, and what we are going to see is the following. We're going to count 6 times the area of the triangle, because know that with each lune we're going to count 1 time the area of the triangle. So if we zoom all the lunes, what we're going to have is the area of the spheres plus 4 times the area of the triangle. Now 6 times, because we need to count 2 times to take into account this into the area of the sphere. So what we're going to have is that the sum of the area of the 3 lunes is going to be equal to the area of the spheres plus 4 times the area of the triangle. So that is that we know that for each one the area is this. So we're going to have that I divided by p plus b divides by p plus c divides by p times 4 times p times r to the 2 is going to be equal. So let us know that these correspond to the area of the 2a's, this to the area of the 2b's, and this to the area of the 2c's, times 4 times p times r to the 2 obviously is going to be equal to the area of this sphere plus 4 times the area of the triangle. So from here we can see another interesting property. What we're going to see obviously is that this is going to cancel, and dp also is going to cancel here, and we are going to see is a plus b plus c is going to be equal times r to the 2, excuse me, times r to the 2 is going to be equals to p times r to the 2 plus the area of our triangle. So what we can do here to see another interesting property is to divide by r to the 2, and we're going to see is that a plus c plus b is going to be equals to of 2p times another number that's going to correspond to the area of a, b, and c divided by r to the 2. So we can deduce from here that a plus b plus c is going to be greater than 180 degrees. Another interesting thing that we can see from here is always what we want. We can subtract p times r to the 2 in both sides and obtain that the area is going to be given to a plus b plus c minus p, yeah, times r to the 2, that's going to correspond to the area of our triangle. This comes from here. So in this way we can name this dxs because of the relationship that I have with planar geometry, that normally we get a sum of 180 degrees and we have here an excess. It's only to relate it with something that we know, and we have that the excess times r to the 2 is going to correspond to the area of the triangle. So in this way we have to do some interesting properties, and in the next video I'm going to talk about transformation between coordinates of Cartesian coordinates to spherical coordinates, to a type of spherical coordinates. That's going to be very important because it's going to permit us to deduce interesting relationship between the sides and the angle. So see you later.